Hello teachers, and welcome to a brand new chapter, Introduction to Logic and Sets. And the very first section we're going to cover today is section 2.1, which is a very fast introduction to logic, but it covers the basics of logic all the way around. So in section 2.1, we're going to talk about quantifiers and their effects on statements, different forms of statements and what a statement actually is, how to determine whether two statements are logically equivalent, how to develop logical arguments, and how to determine whether an argument is valid. That's a lot to do in one section, but we're going to be able to knock it out. I'm going to start with the definition of a statement. And a statement is a sentence that is either true or false, but not both. Both would actually be a paradox, but when I say it's true or false, when you read a statement, if it's possible to determine if it is true or false, it's considered a statement. If you can't decide whether it's true or false, likely it's not a statement. So let me show you an example. Today is Saturday is a statement. Whether today is Saturday or not, that's not the issue. Can you prove that it is either Saturday or it's not? Is that something that could be proven true or false? And for me, today is Wednesday, so it is not Saturday. For you, it might be Saturday, but either it's true or it's false, so it's a statement. On the other hand, teach your class is not a statement. That can't be proven true or false. If somebody tells you to teach your class, that's a command, and it's not considered a statement at all. All right, now we have this other thing called a negation, a statement with the opposite truth value of the given statement. So you just change the truth value. So the negation of a true statement is a false statement. The negation of a false statement is a true statement. So we're back to today is Saturday. For me, because it's Wednesday, that's a false statement. To negate that, I could say today is not Saturday. You see what I mean? Let's do some more examples like that. It says negate each of the following statements. Now, first of all, is that even a statement? 2 plus 3 equals 5. It looks like a mathematical equation, doesn't it? But we can say this is either true or false. And this one is true, right? We all know 2 plus 3 is equal to 5. So let's negate it. It really is as simple as you're thinking to say the opposite truth value of this true statement. We could just put a line through the equal sign, and that has negated the statement of 2 plus 3 equals 5. Now, I don't want you to always get the impression you just draw a line through it, because if you are negating less than or greater than or less than or equal to or greater than or equal to statements, it works a little different. It just means the opposite truth value, though. How about the next one? A hexagon has 6 sides. What would you guess the negation of that is? How about a hexagon does not have 6 sides? I'm thinking that sounds good. A hexagon does not have 6 sides. That is definitely the negation of a hexagon has 6 sides. Does a hexagon really have 6 sides? It does. Yes, it does. Okay, let's move on. Quantifier. Words such as all, some, every, there exists, and no or none are considered quantifiers. Now, another definition of that, what do we really do in here? If we say words like all or some or every or there exists, you might even hear there is at least or there is no more. We're talking about how many of something there is. So all means all of them, none means none of them. But some, we don't know how many that is, but we know it's not it's not none, right? So a quantifier is just trying to talk about how many of something exists. And there are 2 types of quantifiers. One of them is called a universal quantifier. And universal applies to every element in the set. So when you're talking about everything or nothing at all. So all is everything in the set. Every is everything in the set. No is none of the values, or none is none of the values. So those are all called universal quantifiers. where the other one is called an existential quantifier. And that really applies to not all, but some. Like, for example, there exists at least one, or some, or let's stick with that. Those are the most popular. Let's just stick with that. Okay. Now, we got another example. Example 2. Negate each of the following regardless of its truth value. Now, notice both of these examples have quantifiers. So the first one, all students like hamburgers. Remember, all is a universal quantifier. Now, when you negate a universal quantifier, then you go to an existential quantifier. So all students like hamburgers. The opposite of that is not some students like hamburgers, or no students like hamburgers. I'm sorry, I said that wrong. So let me clarify. The negation of all students like hamburgers is not no students like hamburgers. I know it seems like it ought to be, but you're looking at it as black or white. There's some gray in the middle. The negation of all students like hamburgers is some students do not like hamburgers. Now, it might be all the students do not like hamburgers. That does include that when you say some students do not like hamburgers, but again, it's confusing. But the negation of a universal quantifier is an existential quantifier, where the negation of an existential, which is our next example, is a universal quantifier. Okay, so you're trying to change the truth value. So if every student liked hamburgers, the negation of that would be there are people that exist that don't like hamburgers. So some students do not like hamburgers. Okay, again, high point of confusion. I'll make sure you're okay with this. Some people like mathematics. Okay, and you know that's true. I do, right? Some people like mathematics. The opposite of that is not, or the negation is not, some people do not like mathematics. That doesn't pick up the opposite truth value. But the negation of that is, now let's think about it. It's got to be a universal quantifier. So all or none. And you could say it one way. Like my first thought was all people do not like mathematics. That means the opposite thing. Another way to address that is no people like mathematics. Again, an existential negated turns into a universal. So you're speaking about everybody. So maybe go back and look at that again when you try the homework. I think you'll have an opportunity to address that. If you find it super confusing, let me know and we will address that a little deeper. Okay? Now we're supposed to negate each of the following regardless of its truth value. So we're trying to negate this statement. So there exists a natural number n such that 3n equals 6. Right, that's our first problem. Now, again, remind me, what kind of quantifier do we have here? Is this a universal there exists, or is this an existential? Well, it's an existential, right? It's just speaking of some of the items, okay? Not all of the items. So there exists a natural number, and the items in this case is a natural number. All right, so the negation of this is going to be a universal quantifier. You're going to speak about all of them. And the answer, you could say, is for all natural numbers, 3n is not equal to 6. So notice we go to the universal and we change the truth value of 3n equals 6 to 3n is not equal to 6. Also can be a confusing point. Let's try it again. So for all natural numbers, 3n equals 3n. And this is a true statement, right? It doesn't matter what number you plug in for n right here. It doesn't matter at all. This is true because 3n equals 3n. Whereas up here, we should have addressed this. 3n equals 6. The only number that works is 2. It's the only number that works. So to negate that idea, for all natural numbers n, 3n is not equal to 6. Okay, so back over here. For all, the negation of that is going to be an existential quantifier. So how about there exists, okay, a number such that 3n is not equal to 3n. Well, let's see if that's the way we did it here. Yeah, there exists a natural number such that 3n is not equal to 3n. So stop yourself for a minute and let's think about this again. Universal quantifiers turn into existential quantifiers when you negate, and you also change the truth value of the statement. So that's a guideline to get you there, and vice versa. Universal quantifiers turn into existentials, and you change the truth value of the statement. Now I got something new for you. Truth tables. What in the world's a truth table? Hopefully you have done something like this in the past, but if not, brand new, that's okay. It's just going to go fast. A symbolic system to show all possible true, false patterns for a statement. This is the truth table for a negation. So P, y'all, P is just a statement. Like, for example, today is Saturday. That's my statement. Now, if today is Saturday, and for you it might really be Saturday, if today is Saturday is true, then the negation of that would be false, right? Okay. On the other hand, if today is Saturday is false, like it is for me because it's Wednesday, then the negation of that would be true. So notice it just changes the truth value. And then we've got these other things, not just negation. The next thing on my list is something called a conjunction, okay? A compound statement created from two given statements using the connective and. Okay, so again, the key thing here for conjunction is there's an and in between, and the symbol for a conjunction is this symbol right here. Now, how do I remember that? It almost looks like an A for and. It's just missing the little line, so it's just it's like a capital A without the line going across. Anytime you see that symbol, it's and. Now, what in the world is and? Now, when you think about what and means, okay, like today is Saturday and we're going to go shopping. So, and means for the whole statement to be true, they both would have to be true, right? And means both things. So look at what's going on here. And I also want to encourage you to do truth tables this way every time. If you have to do a truth table, then if you let P, the first column, be true, true, false, false, and then you alternate Q, true, false, this will set you up to do a good truth table, because what you're trying to do is combine these every way possible. So P true, Q true, P true, Q false, P false, Q true, and P false, Q false. Do you see what we have going on here? That's every possibility. Do they have to be in the same order every time? It's a real good idea, okay? They don't have to be. You can organize these however you want as long as you list all four possibilities. But my advice is to do it this way because every book I've ever seen does it this way. Okay, now, the outcome for an and. Notice if you have true and true, the answer is true. That is the only time an and is true. Look at the other situations. If you have a false with an and statement, think about it. If today is Saturday and we're going shopping, but today is not Saturday, then that's a false statement because today is not Saturday and we're going shopping. It can't work out. And so if one of the statements is false, or either both of them are false, it is false all the way down. So a true statement is only true, or an and statement, I'm sorry, is only true when both are true. Very important. Now let's take a look at something called a disjunction. So a conjunction is an and, a disjunction is an or statement. So anytime you see an or statement, that's a disjunction. Notice what happens with the symbol there. It's a V. Okay, it's really the upside down of an and. It's a V. So again, and is like an A without the line, and an or is upside down, kind of like an R. If you get lazy writing your R down, it could almost start looking like a V. There you go, or, okay? Now look at the truth table again. If you've never done these before, this PQ business is a little weird. Notice how it went true, true, false, false for my P's. Then my Q's went true, false, just like the last table. But now what does OR mean? Okay. Now if you're a mama, what OR probably means to you is one or the other, but not both. For example, if you're giving your child options between two things, usually both is not on the table. But in math, this is called an inclusive OR, and it does mean one or the other or both. And again, that can hang you up a little bit. Be careful with that. So if P is true or Q is true, that means the whole thing is true. But even if one of them is false, the whole thing is true, because what you're after is one of these values to be true. Look here, one of these values is true. So for an OR, if one of the values is true, then the OR statement is true. But notice the only time that an OR is false is when both statements are false. You with me? Unlike an AND, the only time it's true is when both are true. An OR, the only time it's false is when both are false. So now we have a negation, a conjunction, a disjunction. I'm not even done yet, but let's do some examples. All right, so example 3, classify each of the following as true or false. Now, before we get started, we need to look at these statements. Are they really statements? Well, first of all, mathematical equations are statements if they're all numerical. Like, for instance, 2 plus 3 equals 5. Actually, they're statements even if there's variables in there, but it's dependent on the value of the variable, their truth value. But 2 plus 3 equals 5. Okay, true or false? Well, that's a true. Let me get my pen working. That's a true statement, right? 2 times 3 equals 6. Yep, that's a true statement. On the other hand, 5 plus 3 equals 9. That's not cutting it, right? 5 plus 3 is equal to 8. So that's a false statement. Now what we're after here for question A is P and Q. Okay? So and, remember, when is an and true? Only when they're both true. So another way to think about this is P is true and Q is true. Then we can say that implies the whole thing is true, and just we're using T to represent true, but the real answer is the word true. Now I've got that typed up for you in a little more detail. Here we go. P is true and Q is true, so P and Q is true. Now let's try this same thing for R. Okay, my values disappeared. So again, P is true. I didn't mean R, I'm sorry, for question B. Q is true. Again, we know R down here is false. So they're asking us an OR. So Q, I'll look up here, that's a true statement. R, that's a false statement. And does that mean we're false? No. Remember, with an R value, as long as one of these values is true, hey, the whole statement is true. So once again, this implies this entire statement is true. Now the typed up version of that, here you go. Q is true, and did I do that right? Yeah. I didn't realize I put R down. I apologize. I'm changing the screen too fast on you. Q is true, and R is false. So Q or R is true, because an OR only requires one of them. Now the next one. See if you can do this one on your own. Pause it real quick. See if you can do C by yourself. Alright, so we're looking at this. Again, my truth values have disappeared. 2 plus 3 equals 5 is true. 2 times 3 equals 6 is true. 5 plus 3 equals 9 is false. Correct? So not P. We're saying not, but P is true, or R is false. Now this requires a little bit of simplifying. Not P, not true right here. This not true is false, right? That's what the little negation symbol in front means, and we read that not most of the time. So not true is false, or false. Remember, the only time an or is false is when both of them are false, and that's exactly what we have here. So not P or R in this particular case is a false statement. Now the typed up version of that, not P is false and R is false, so not P or R is false. Kind of getting the hang of this stuff? Let's do another problem. Okay, classify each of the following as true or false. Here we go again. So again, my advice, why don't you pause the video real quick. Try these three on your own. They're slightly more complicated than what we just did, but I promise you, try them, you can do it. And you come right back and we'll do them together. Okay, so I think we would find it helpful if we put the truth values under here again. So P is the statement 2 plus 3 equals 5. That's true. Q is the statement 2 times 3 equals 6. Also true. But false is still, R is still that statement 5 plus 3 equals 9, which is a false statement because we know 5 plus 3 equals 8. Now, you can substitute directly in this expression. So not P, so that's not, and P is a true statement. And not Q, so not, and Q is a true statement. Then if I had room underneath, I would keep going down, but I'm doing these little arrows across to just help you follow my logic. Not true, or the negation of true, is false, right? And the negation of true is false, and we know a false and a false it's not true, right? A false and a false is overall a false statement. Now I have all these results typed up too, but let's go ahead and do them by hand together. Okay, and notice this time the negation is out front. Is that okay? Sure it is. What this means is you do the inside first. You know order of operation. It applies to logic as well. So not, or the negation, and then P or Q. So P is a true statement, or Q is a true statement. Now again, if we are doing the inside of the parentheses first, the negation stays outside. And what's true or true? Well, for an and or an or, it doesn't matter. Two trues together just gives you a true. Okay, but then we do the negation of true, which gives me a false. And so that is the end of that one. All right, for the third one, we have P or Q. So I'll look up P is a true statement, or Q is a true statement, and then and not R. Now R is a false statement. Again, how do I handle all this? Well, let's just work on one part at a time. In the parentheses first, a true or a true is overall true. So I'm not going to write parentheses anymore. I have handled all of that. Now I still have the and symbol I got to deal with. And not false, y'all. We know not false is true. And then how about this true and true? Well, true and true is always true. Look at there. I tried to write false. It's always true. So that's the handwritten version of this. We're going to go through the typed up version of this, which is addressing it just more in word form. So here I go. Again, not P is false, remember, because P is true, and not Q is false because Q is true. And then if you have false and false, overall that's false. Just like we did it, just in words here. I think the symbols are much easier to understand, but I'm a math person all the way around. So look, they handle the inside. P or Q is true because P is true and Q is true. So not P or Q is false. And then the third, they address, notice P or Q is true. We'd already done P or Q. And not R is true. And if you have an and, okay, in between them, true and true is overall true. All right, so we've become comfortable with a negation, a conjunction, which is and, a disjunction, which is or. Now let's move on to a new guy. It's called a conditional. So here we go. Conditional. They also call this an implication. I think they call it an implication. I'm not used to reading this called an implication. Conditional is what I know it as, but you often read this as implies, okay? So it's a statement expressed in the form of if P, then Q. A lot of computer language uses these if-then or conditional statements. So if P, then Q, and notice the notation for that. So this is how you read it. This is how you say it out loud, and this is the notation. Okay, notice they say the hypothesis is the if part. I've also heard that called the antecedent. The conclusion is the then part. Okay, all right, now check it out. Look at your P's and Q's just like we set it up before. True, true, false, false for your P values. Your Q values are true, false, true, false. And then you do if P, then Q. Okay, so if true, then true is a true statement. Okay, so if the hypothesis is true and the conclusion is true, that means the whole statement must be true. But check this one out, and this is the one you got to really pay attention to. Okay, if the hypothesis is true but the conclusion is false, that is the only time a conditional statement or an if-then statement is false. But now look at the third and fourth one. Isn't that weird? If the hypothesis is false and the conclusion is true, hey, it's just a true statement. And really that if you made up your own example, I think you might see better why that's the case. If the hypothesis is false, you can't really speak to the truth value easily of what's happening. So you're just going to say it's true. And even the strangest case, if the hypothesis is false and the conclusion is false, then the statement is true. Because again, if the hypothesis is false, then really, what do you really know in the first place, right? So again, this blue one is really important. If your hypothesis is true, but your conclusion is false, that's the only time you get a false for a conditional statement. Let's go over one more idea, or maybe four, before I shut this video down. It will go to a part 2. So any implication, again, there's a couple ways you can read these. If P, then Q, or you could even read it P implies Q. That's why they call it an implication. Has 3 related implication statements, okay? One is the converse. So notice if you have P then Q, the converse flips it around. So you don't just read it backwards, but you put the if in front of the then statement and the then in front of the if statement. Okay, so it's if Q then P, and notation-wise is if Q then P also. So notice the arrow flips around. Now, inverse is the negation. So notice with the inverse, I'm going to change my highlighter color, the order, P then Q, stays down here, P then Q, but you negate both of them. So if not P, then not Q gives you this. Now, I had a clever student one time tell me to help her remember this, the inverse one has an N in it, and a negation has an N in it. And so I think that helps me, actually, because it's easy to get these mixed up. Converse is like the same as reverse. But inverse, you keep the order the same, you just negate both statements. So you start with if P, then Q, then it's not if not P, then not Q. Now the contrapositive, this guy's fun, you do both things. Let's say, okay, so for a contrapositive, notice it says if you start with if P, then Q comes first, but it has the not also. So if not Q, then not P. And so again, there's the notation for you. If not Q, then not P. All right? Now, when you see this in action, I think you're going to feel a little bit better about it. So converse, you change the order. Inverse, you keep the order, just change the negation. Contrapositive, you do both of those things. Okay, so let's do this example and then shut this video down and come back and finish section 2.1 in a part 2. It says write the converse, inverse, and contrapositive for the following statement. This you can do. If I am in San Francisco, remember that's like your P statement. So if I am in San Francisco, oops, pen not working. If I am in San Francisco, then I'm in California. So P is like your I am in San Francisco, and Q is like I am in California. So if P, then Q. Converse, remember, you flip these guys around. So in your mind, do that. That means if I am in California, then I am in San Francisco. Notice you don't keep the if with San Francisco and the then with California. You switch the order around, and the if goes with California, and then the then goes with San Francisco. So typed up, if I'm in California, then I am in San Francisco. Now, let's think about the logic of this just real quick, right? If I am in San Francisco, then I am in California. Does everybody agree with that? Back to, geography, right? San Francisco is in California, so that's a true statement. If P, then Q is actually true in this case. Now, the converse, is it true that if I'm in California, then I am in San Francisco? Well, absolutely not, right? What if I'm in LA, right? Or San Diego? Okay, so the converse appears not to be true if the original implication statement or conditional statement is true. Keep that in mind, okay? Now let's do the inverse. Remember what inverse means? Think in is negation. Yes, you keep the order the same. So if you keep the order the same, you're just negating. So how about if I am not, remember add the not, if I'm not in San Francisco, then I am not in California. That is your inverse. If I am not in San Francisco, then I am not in California. Now, back to just thinking, right? Logically, does this make any sense? If I am not in San Francisco, does that mean I'm not in California? Nope. If I'm not in San Francisco, I might be in San Jose, right? There's a San Jose, California. There's one in New Mexico. Let me try that again. If I'm not in San Francisco, I might be in LA. I know that's in California. Then I am not in California. So that doesn't make any sense either. It really doesn't make any sense. Now, I might not be in California, but just because I'm not in San Francisco doesn't mean I'm not in California. All right, contrapositive. Remember what you do for the contrapositive? You do both, okay? So you change the order, which is called converse, and you negate both of the statements, which is called inverse. And so when you do both, it's the contrapositive. So here we go. If I am not in California, then I am not in San Francisco. Now, how about that, y'all? Does that mean the same thing as if I'm in San Francisco, then I'm not in California? Now, first thought might be not, but does it make sense? If I'm not in California, then I am not in San Francisco. Sure enough, right? If you're not in California, there's no way in the world you could be sitting in San Francisco. So it turns out, this is no proof, by the way. All this is just an example. So I'm telling you a conclusion, not based on this example, but later on we could do a proof for this. But the original statement, okay, so the original if-then statement, it's called a conditional, and the contrapositive have the same truth value. Hey, it also turns out the converse and the inverse have the same truth value. So these two things are saying the same thing. And when we talked about the logic behind them, just what those statements means, they actually do mean the same thing when you think about it. Okay. All right. I'm going to shut this video down. It went about 3 minutes over my requirement. I'm going to come back and wrap this up. Hopefully it won't take 30 minutes in part 2, but we do have some more logic to continue to talk about. If I don't talk to you again today, I hope you have a wonderful day, and I'll see you back next time.